When we look at stars with a spectroscope, we see distinct dark bands. Some stars have more, some have fewer, but with every star there is always the same pattern containing 4 dark bands. What are these bands, and how are they created? Well, those lines aren't random. To astronomers, they are like fingerprints, but for elements. To understand why these lines appear, we can start by looking at the simplest element on the periodic table, hydrogen. Hydrogen is especially useful because of its simplicity. A hydrogen atom has just 1 proton and 1 electron, which makes its behavior easier to predict and model than more complex atoms. Electrons and atoms can only have specific energies. These are called energy levels. These levels are determined by the structure of the atom itself. So if hydrogen gas is given energy, such as from heat or electricity, its electron can jump to a higher energy level. But this excited state is unstable, so the electron soon falls back down to a lower level. When the electron drops back down, the extra energy does not disappear. Often it is released as light. The wavelength of that light depends on how much energy was lost during that transition. Because electrons are restricted to specific energy levels, only certain energy transitions are possible. As a result, hydrogen emits light at specific wavelengths. To the naked eye, the light hydrogen emits looks pinkish purple, but when that light is spread out using a spectroscope, it separates into a series of bright lines. This pattern of bright lines is called the hydrogen's visible emission spectrum. Not all electron drops produce visible light, but in hydrogen, when an electron drops to the second energy level, the light produced happens to be in the visible range. This is why several visible lines appear in the hydrogen spectrum. When an electron drops from the third energy level down to the second, hydrogen emits red light at 656 nanometers. A drop from the fourth energy level to the second produces blue-green light at 486 nanometers. A transition from the fifth energy level to the second releases violet light at 434 nanometers. Finally, a drop from the sixth energy level to the second produces deeper violet light at 410 nanometers. Together, these 4 lines make up the visible portion of the hydrogen emission spectrum. This is called the Balmer series. This pattern exists because of the structure of the hydrogen atom itself. But stars usually don't show bright emission lines, they show dark lines. So how are those dark lines created? When light with a continuous spectrum passes through hydrogen gas, the atoms absorb the specific wavelengths they would emit if energized. For example, an electron can absorb just enough energy to move from the second energy level up to the third, removing red light at about 656 nanometers from the spectrum. Although the atom releases that energy, the light is emitted in a random direction instead of continuing towards the observer. As a result, that wavelength is missing or greatly reduced in the light that reaches us, creating a dark absorption line. This direct connection between emission and absorption spectra allows scientists to identify hydrogen even when it's not glowing on its own. Because hydrogen is the most abundant element in the universe, its spectral lines appear frequently in light from stars, nebula, and galaxies. These lines can act as reliable markers, allowing astronomers to identify hydrogen across vast distances and use it to study the structure and behavior of the universe. Sometimes, though, when we look at very distant sources, that same pattern appears, but not where we expect it. If you want to discover why that shift occurs and what it can tell us, exploring redshift is the next logical step. Thanks for joining me on MN Horizons.